Hey AP Stats, we are going to do the first part of Chapter 8 notes today. And specifically, we're going to be talking about the binomial distribution. So binomial, you've probably seen somewhere along the lines in your math history, but we're going to talk about the binomial distribution, which you probably haven't seen, okay? So just the form bi, what does that mean? Bi means 2. Okay, so in a binomial setting, we are looking at 2 outcomes, usually considered a success or failure. Okay, typically we're looking for the number of successes. Okay, so there's 4 requirements for a situation to be considered a binomial setting. Okay, so make sure you know these. It often can come up where it asks you to verify something's binomial, and you would have to show all 4 of these are true. Okay, so each observation falls into one of just 2 categories. A success or a failure. Okay, so that doesn't necessarily mean that there's only 2 outcomes that can happen. So for example, if you're going to roll a dice, and I'm just looking at, a standard dice, 1 through 6 are the outcomes, but I'm looking to roll a 5. So here I could consider my success when I roll a 5. My failure would be not rolling a 5. Okay, so you can set up things where there are more than 2 outcomes, but you just have to classify what you're going to consider a success and what would be the failure. Okay, there is a fixed number of observations, so you know how many times I'm going to roll a dice, for example. The n observations are all independent. Okay. The probability of success, call it P, is the same for each observation. Okay, so it doesn't change. And a binomial setting, they're used with a discrete random variable. So those 4 things. So technically, if something's a binomial setting, then you get a binomial random variable, and then it follows a binomial distribution. Okay, so those are just the vocabulary. The shorthand notation for binomial is the capital B, and then N and P is what you would list inside there. So are the following binomial settings. Example 1, blood type is inherited if both parents carry genes for the O and A blood types. Each child has the probability 0.25 of getting 2 O genes and so having blood type O. Different children inherit independently of each other. Let X equal the number of successes of having blood type O for 5 children. Is this a binomial setting? Okay, so to determine if it is a binomial setting, we need to just verify those 4 conditions above. Okay, so does it fall into just one of 2 categories, success or failure? So is the number 1, we'll bullet point for number 1 true? Yes, it is. Okay, so they either have blood type O or not. Okay, we don't care what other type, we just know they either have O or not. Is there a fixed number of observations? Do we know, in this case, we're talking about kids, how many kids there are total? So yes, it tells us there's 5 children. So yes, 5 children, 5 outcomes is what we're looking at. Are they going to be independent? Are the N observations all independent? Yes, they told us the children inherit it independently. So yes for independence. Number 4, the probability of success, is it the same for each time we do it? Yes, P stays the same, and it equals 0.25. Okay, so this would be yes, binomial. All right, number 2, deal 10 cards from a shuffle deck and count the number of red cards. there are 10 observations and each gives either a black or red card. A success is considered a red card. Is this a binomial setting? Okay, so let's look at, does each observation fall into just one of two categories? We have that, yes. We have, it's either a red, which is our success, or black. Okay, so we've got that. Do we have a fixed number of observations? Yes. We've got 10 cards. So we're looking at X is the number of red cards in those 10. But the other two conditions are they independent, and does the probability stay the same? Do those hold up? No, because we're dealing these out without putting them back into the deck. So once you take a red card out, that changes the probability of getting another red card. And once you take, 5 cards out of the deck, that changes the probability that the 6th card will be red. So they're not independent, and the probabilities change. So for that reason, this is not binomial. Okay. Sometimes we will assume independence in this case when n is really, really big. So a lot of times when we're taking like a survey of a population or like a very large sample, we're actually not putting those people back in, because if we survey them, we've talked to them and we don't want their opinion again. We'd want somebody else. So we don't actually replace them. But when your sample size is really, really large, then we can get away with that, just so you know. So sometimes that does come up. Okay, number 3. Each child born to a particular set of parents has a probability of 0.25 of having blood type O. If these parents have 5 children, what's the probability that exactly 2 of them have blood type O? Okay, so blood type O, 2 of the 5. So basically we want 2 successes and 3 failures. Okay, so over on the side, I'm going to kind of show you. We want 2 successes and 3 failures. So if we talk about success is blood type O, and I'm just going to say the failure is, I don't know, N, not O. So if we think back to like when we were tossing coins and looking at heads and tails and writing all those out, we have like a success, and then like not O. But it doesn't have to happen in that order. It does not. Does it have to be the first 2 kids? No, it can be in any order. So we would have to rearrange this over and over and over again. Do we remember how many arrangements? So like if I write another one, it would look like this and so on. And you have to do all of the different orders. Do you remember how many there are of these? Where does that number come from? Any ideas? We talked about this a little bit. I feel like we should have. And sorry, normally I do this on the whiteboard on the side, so you can see this on the side of the problem. But how many different arrangements comes from the Pascal's triangle? So if I can draw it over here on the side for you. So I'm running out of room. Okay, so it kind of got squished. But we're on this row because we're dealing with 5. Okay. Oops, sorry. There should be another 10 in there. That's why it's off. Oh, hold on. Let me fix that. Okay, so there. Sorry. I had to fix that. So when you're looking at Pascal's triangle, this would be like when you have 5 events, there could be like 0 heads, then you could have 1 head, 2 heads, 3 heads, 4 heads, 5 heads, okay? So when we look at this, this would be like 0 successes, 1 success, 2 success. How many successes are we having here? 2. So there's going to be 10 different ways that we can rearrange this. Okay, so our probability, we've got 10, then our probability of success, we know they're independent, so we're allowed to multiply them. What's the probability we're considering that they do have blood type O? Going to be 0.25. So we're going to have 0.25 times 0.25 for the 2 successes. Okay, it's just looking at like this order right here. And then what's the probability of failure then? If the probability of success is 0.25, what's the probability they don't have blood type O? Yeah, 0.75. So we'd have 3 of those. So these are our success, success, failure, failure, failure. And then they can happen in 10 different arrangements. So we have to multiply it by 10. So this is the same thing as 5 combination 2. Okay, those are all combinations. That's what comes from Pascal's triangle. Okay, so when we calculate that, go ahead and grab your calculator if you don't. You definitely need it for today. So go ahead and multiply that out. Okay, so grab your calculator and multiply it out. So you should get 0.264. Okay, so I'm going to show you how this works. This is the same thing as our formula. So probability x equaled 2. We had 2 successes. That 10 came from the 5 combination 2. Our probability of success was 0.25, and we had 2 of them. And our probability of failure is 0.75, and we had 3 of them. Okay, this is the binomial formula. Okay, so I kind of didn't give you too many problems like this in our probability chapter because it's so much easier to solve them using rules of binomial. Okay, so there's a couple things you want to see. You got 5 combination 2, so this is always going to be the number of successes. Okay, this is your probability of success. That's your probability of failure. And then these numbers up here, this is how many successes, and this is how many failures. Okay, so this is the number of successes, and this is the number of failures. So those always have to add up to your total. So we have 5 altogether, so we have to have 2 successes, 3 failures. So that's always, those exponents will always add up to however many you have, so 5 in this case. And your probability of success and failure should be opposite, so they should add up to 1. Okay. So here's your official definition. It looks a little different with all the different symbols in there. So like this is what we just looked at over here on the right. Probability x equals k. You have n combination k. P is your probability of success, so p to the k. 1 minus p to the n minus k. Okay. So that is what we just wrote up there. This though, I put this other formula on here because this is how it's shown on the formula sheet. And it looks like this, where you how you say that is n choose k, which is the same thing as a combination. Okay, but I just want you to see that because this is how it is displayed on the formula sheet for the AP exam. Okay. So this is one of the formulas that's on there too. Okay, so let's try some problems. An insurance salesperson is able to sell policies to 15% of the people she contacts. Suppose she contacts 10 people in 2 hours. What is the probability she sells exactly 2 policies? Okay, so let's list some of the things we know. What's our 10 people? 10 people total, so that's our total, which is going to be n, so that's 10. What's our probability of success here? That's p. Probability of success can be 0.15. And then k is what we call the number of successes. How many successes are we looking for? 2. Exactly 2. Okay, so those were our numbers, so where they came from. So let's write out this. So what's the probability that she has 2 successes? Probability x equals 2. We're going to do our combination. So our total 10 combination 2. Probability of success is 0.15, and we're going to have 2 of them. So then what would be the probability of failure? It's the opposite of 0.15, so we get 0.85. And then how many failures must we have? If we have a total of 10, 2 successes, we've got 8 failures. Okay? So this 10 combination 2, you can put in your calculator. Let me just remember where it is. You have to put the 10 first, and then you go to, so to get this in the calculator, you would write 10, and then go to math, over to PRB and grab the NCR button, okay? And then enter 2. And that will get you just that combination. So this should equal 45. So you got 45 times 0.15 squared times 0.85 to the 8th. So go ahead and calculate all that. Okay, so you should get 0.276. Okay, so on the AP exam, if you have a free response question, you always need to show your work like this using the formula. But if it's a multiple choice question, I'm going to show you a shortcut in using the calculator commands to do that. Okay, so you do need to know the formula, but if you flip the page, we're going to go over some calculator commands. Okay, so the calculator commands, we've got 2 of them. We've got binomial. We're talking about binomial distribution, so it's either a PDF or a CDF. PDF goes with 1 probability, okay, where x equals a value. CDF is cumulative, so it does less than or equal to. Okay, so that's what the CDF is. Okay, so for x is less than or equal to k, we're going to use CDF. When you just want an equal to, then you're using the PDF. Okay, so that's the difference between those 2. These are also in the distribution right below normal CDF. Okay, so you're going to go to second distribution and scroll down. You got to go down, but they're right by normal CDF. Okay, so if you know how to get to normal CDF, you can find binomial PDF and CDF. Okay, so we're going to practice this, but I'm going to have you do kind of a couple easier ones first. So we're going to go a little out of order here. So number 5, in the 2015-2016 season, Steph Curry had a free throw percentage of 90%. Consider his next 5 free throws. So I'm actually going to have us answer a few questions before we do part A. Okay, so let's start with part B. What's the probability he makes exactly 4 of them? So which calculator command would I want to use to get exactly 4? Okay, so our probability x equals 4. And that'd be binomial PDF or CDF. Yeah, we're going to do PDF. PDF is for 1. Okay, so what you stick in there, which you see up here, is n, p, and then however many you want. So n is the total number of shots. So how many do we have here? We're looking at 5. So 5. What's the probability of success that he makes it? We've got 90%, so you're going to put 0.9. Then you put a comma, and then the last one is how many you want him to make. So here in this problem, we're looking at 4. Okay, so we're going to go to second distribution and scroll down, 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 down until you get to, make sure you pick the right one, but you want binomial PDF, okay, the 1 probability distribution, 5, 0.9, 4. Okay, so here you should get 0.328. Okay, were there any calculator difficulties, technicalities? Please help each other out. So go ahead and pause this if we've got questions on where that command is before we keep going. Okay, so if you need help, ask a partner real quick, someone next to you, to see if you can grab that command. Okay, we're also going to jump down and do D next. What's the probability he makes at most 4 of them? So how do you write at most? Probability x, we're going to write less than or equal to 4. Okay, so for this one, we're going to do, we really want to add up 0, 1, 2, 3, 4. I don't want to do binomial PDF that many times. That's really annoying. Okay, so there's a couple ways you can get around that. The only case we're not considering is 5, so you could do 1 minus binomial PDF of 5, that he makes all 5. But the less than or equal to, we have a calculator command that does that for us, and that's where we're going to use binomial CDF. Okay, so binomial CDF, we're going to use the same command actually. It's going to be 5.9 and how many we want it to do. But the calculator, because we're using CDF, it's going to add up 0, 1, 2, 3, and 4 and just stick out the answer for us. Okay, so go back to second distribution and go get binomial CDF, the cumulative one. So we are going to get a very different answer. Well, in this case, not super different, I guess, just because of this probability. Okay, but we're going to sum up those other ones below it, and so you should get 0.4095, so if I round, 0.41. Okay. Okay, we good so far? Okay. So, what's the probability he makes at least 3? We'll go back to part C. Probability he makes at least 3. Okay. So at least is going to be 3 or more. Okay, 3, 4, or 5. So we really want to add up probability x equals 3 plus probability x equals 4 plus the probability x equals 5. I'm not really a fan of doing binomial PDF multiple times. You can do that. It's fine. You'll get the same answer. Okay, so you could do binomial PDF for 3, 4, and 5. But I want to see if I can get the binomial CDF, the cumulative, to work for us. Okay, CDF, like when you look at the definition up here, it only does less than or equal to. So can we get it to do it greater than? Okay, what we're going to need to do is subtract from 1. Okay, so this is the same thing as 1 minus. Okay, what are the conditions I'm not, or the cases I'm not using are 0, 1, 2. Okay, so that's the same thing as 1 minus the probability x is less than or equal to 2. So if you think about the cases over here real quick, let me just show you. So 0, 1, 2, 3, 4, 5. We want 3, 4, and 5 to be in our answer. Okay, so greater than or equal to 3. So that means I need to subtract 1 minus 0, 1, and 2. So that's where this comes from. 1 minus probability x is less than or equal to 2. So here I'm going to do 1 minus binomial CDF, cumulative, 5.9, and I want it to go up to 2. Okay, so the CDF is going to do the 0, 1, 2, then subtract that from 1. Okay, so go in our calculators, 1 minus binomial CDF, 5.9, and then 2. So you should get a pretty high number here. So you should get 0.99, like 1. Because his free throw percentage is so high. Most likely he's making a lot of his shots when he has a free throw percentage of 90%. Okay, so the concept of part C is a little bit tricky. Those are always like the harder ones for most students when we're going greater than. And usually the hard part is picking which number you're including here. So I would strongly suggest writing out a little number line like I did over here on this side. It tends to help students a lot. Okay, so going back up to part A, I want to draw out, like we're going to make like a histogram of the probabilities. Okay, so his option, if he's making 5 free throws, he could make 0 of them, 1 of them, 2, 3, 4, 5. So basically I need to find those probabilities for each time. So these are each binomial PDF problems. We're finding exactly, you know, he makes 0 shots, 1 shot, 2 shot, and then 2 shots in any order. So these are all binomial PDFs. And I'm actually going to do this in the list. The only bummer is you guys can't see what I'm doing in the calculator. But I just want, because I want to calculate binomial PDF over and over again. So, I mean, you don't have to do it in the list, but it's basically 5.9, oops. Oops, sorry, I don't know what this thing is doing. I just needed an eraser. Okay, sorry. So 5.9, and then we're going to insert, we want to insert 0, and then 1, and then 2, and then 3, and then 4, and then 5. Okay, so in the list, I'm just going to do this because I like using the list and I'm less likely to make mistakes. So in list 1, I'm going to do 0, 1, 2, 3, 4, 5. Okay, and then in list 2, I'm going to show you what I'm going to do. So go to Stat, Edit, List, so clear out if you have old stuff in there. So list 1, do 0, 1, 2, 3, 4, 5. And I mean, you don't have to do this in the list. I just think it's easier just because it's going to do it over and over again. So I'm going to go up to where L2 is highlighted. Okay, and we're going to do this. Binomial PDF 5.9. And what am I going to stick in this blank? I want it to do it for 0, 1, 2, 3, 4, 5. That's where I put. And so I'm going to stick in L1. So I go up to L2 is highlighted. Go to second distribution, binomial. Make sure you get PDF. Okay, and then we're going to do 5.9, comma, and then do L1. So the only reason I did it in the list is that it's going to give me each of those probabilities, and it's very easy for me to then draw the histogram. Okay, so you can see the probability he makes all 5 shots is pretty high, 0.59. And then like from 0 to 3, they're all like really small. So I'm just going to 0, 1, 2, 3. And then at 4, we're up to like 0.33. Okay. So don't stress over this too much about graphing that, but you would use binomial PDF. I like to use the list, but you again don't have to. You just have to find binomial PDF for each one of those numbers. Okay, so let's try one more problem here. Okay, so we can practice these binomial calculator commands. So 60% of all computer monitors sold by a large computer retailer have a flat panel display, and 40% have a CRT display. Okay, so this info is super old. You guys probably don't even remember what a CRT display is. It's like with the really big, bulky ones. And the type of monitor purchased by each of the next 12 customers will be noted. Let X equal the number of monitors among the 12 that have a flat panel display. So X, what we're considering a success, is defined for us, the ones that have a flat panel display. So we have our N is 12. We're looking at 12 people. We have, what's the probability that they have a flat panel display? Careful, they said 40% have the CRT. So our probability of success is not the CRT, it's the opposite. So 0.6. Oh, and they gave that to us up here. 60% have the flat panel. Okay, so part A. What's the probability that we have exactly 4 monitors are flat panel displays? So this probability notation you also want to include. So probability X equals 4. The calculator command we want to use, excuse me, is the equal to. So we want binomial PDF. We're going to do 12. Probability of success is 0.6, and we want 4 of them. So go ahead and put that in your calculator. Okay, so go grab the binomial PDF. Grab that. Okay, so this, we're going to have 0.042 is what you should get. Okay, between 4 and 7 inclusive. So that means we're including 4 and we're including 7. So probability X is between 4 and 7. So this is the probability X equals 4, X equals 5, X equals 6, and X equals 7. Okay, there's a couple ways that you can solve this. You can do binomial PDF of 4, 5, 6, and 7, just add those up. Totally fine. There's also another way that you can do this. Okay, so there's always going to be multiple ways that you can solve this. I'm going to show you another way to do this. So if we're looking at our numbers, our options 0, 1, 2, 3, 4, 5, 6, 7. And we actually go higher because our total is 12. So 8, 9, 10, 11, 12. I want 7 to 4. Okay, so one way I can do this is to do binomial CDF, cumulative. 12.6, and I'm going to do 7. So what this is going to do, but this is going to go 7 all the way down to 0. Okay, that's a little bit too much. I don't want all the ones all the way down to 0, so I need to subtract off these ones. Okay, so I need to subtract binomial CDF 12.6, and I need to subtract off 0 through 3. So I'm going to put a 3 here. Okay, if that seems complicated, don't worry about it. We'll talk more about that when I get back. But this is the way that I would set it up. You could do binomial PDF of each of those numbers instead. Okay, so you go ahead and calculate that however you want to calculate it. Okay, so here you should get 0.547. Okay, and then for C, between 4 and 7. So we're not including 4 and 7 here. And because this is discrete, it's a discrete probability distribution, that really just means we're talking about 5 and 6. So you can solve it the same strategy we did in part B, or you could just do binomial PDF, the individual one, of 12.6 and 5, plus binomial PDF of 12.6, sorry, I'm running out of room, and 6. Okay, so just adding up the 5 and the 6. Okay, so go ahead and type that in your calculator. Binomial PDF, make sure you're using PDF, not CDF, the individual one. Okay, so when you calculate that, we should get 0.277. Okay, and then for part D, what's the probability that more than 6 are flat panel displays? Okay, X is greater than 6. So that's including 7, 8, 9, 10 is what really we want. Okay, so if you think about, I'm just going to write out some of the numbers over here. So it goes that way and it goes all the way down to 0. So we want greater than 6, we want 7 and higher. So what do we need to subtract off? I need to subtract off these ones. Okay, so we're going to do 1 minus binomial CDF, the 12.6, and what do I need to stick in there? I need to subtract off 6 all the way down to 0, so this becomes a 6. Okay. Okay, so I need to subtract off the 6 and lower. So go ahead and calculate that. Make sure you're using CDF as the cumulative one. And you should get 0.665. Okay, so you guys have a worksheet for homework tonight. Do your best on these ones. We'll talk about it when I get back. And good luck with that. Okay, I'm not sure on your worksheet. I forget if you need to know the mean and the standard deviation. There's your formulas right there. But other than that, we'll talk about that when I get back. See you guys later. Bye.